I just built a rack system completely from scratch with no premium embedding model and no expensive cloud vector database. This exact system currently powers a customer service AI agent, and the beauty of it all is that it is completely deployable with your regular backend server. So let's start writing the code. So first of all, we start by creating a visual environment since we are going to be implementing it in Python. The next thing is we activate the visual environment. Now that the environment is activated, so let's go on to install all the packages we need, at least the ones we know for now. Here we have the transformer package, ChromaDB, and these ones. Don't worry about the package, I will explain what each of them what we need each of them for as we go into the tutorial. So while that is installing, let me use the opportunity to give a background knowledge of what a RAG is and what we are going to be doing here. As we all know, since large language models were trained with data from the internet, so they are very good at general knowledge tasks. But when it comes to enterprise specific tasks that involves data they were not exposed to during their training, they are not expected to perform well, like what we have here. Here ChatGPT is saying that it needs more data to complete it, but with the help of RAG, we can bring this data, enterprise data, to the awareness of the model, and that's what we end up having here. So this is a screenshot of a conversation within an AI agent and me. It was an agent I was working on. So you can see here the agent can answer some company specific question, and it can also carry out action like sending a mail, and this is a screenshot of the mail. So to achieve this, there are two general ways to get this done, either via fine-tuning or via RAG system, where fine-tuning is kind of costly, meanwhile RAG is relatively cheaper to implement. Now let's go over the workflow of a RAG system. In a typical RAG system, we basically really want to do two things: to insert data and to fetch the data. But unlike relational database, that the insertion and fetching is done with absolute precision, in RAG systems we do not fetch the data with the intention of getting the exact match. But anyway, we'll get to that. So first of all, the insertion part. So for insertion, our data basically and usually comes as a bulk, and we are not going to be inserting it as a bulk. So the first thing we do is we chunk the data. So chunking the data involves, let's say, given a page, we take individual lines on the page. So we pass each of these lines through a tokenizer. The tokenizer creates what we call token ID for each of the token. By the way, it is easy to visualize a token to be a single word in a sentence, but in reality it's not actually that way. So let's just head over to a website that actually enables us to visualize what a token looks like. In this website, tokenizer.versa.app, it is easy to visualize that in any given sentence, the words that make up the sentence are not necessarily considered tokens, and some words are divided into more than one token. For example, retrieval here is considered 2 tokens, and even augment is considered 2 tokens. So giving a sentence to the tokenizer breaks it into tokens that the embedding model can understand. And note, the embedding model doesn't receive the token but receives what we call token ID, which are the numbers below here. So for example, here this one represents the first part of retrieval, and then this one represents the second part of it. So this is how a tokenizer works and can be visualized. Let's go back to the diagram now. Once we get the token IDs from the tokenizer, we pass it into the embedding model. So the embedding model is basically another large language model that specializes in converting token IDs into embedding vectors. Embedding vectors are the actual item that are stored in a vector database. Remember that a vector database is just a space where similar things are stored close to each other, and the way similar things are known and then stored close to each other are via their embedding vectors. So the numbers you see here are basically the embedding vectors, and they kind of give the precision of the space where each of these token ID should be located. So once the embedding model converts token IDs into embedding vectors, we will now store them into the vector database, and this ends the process of inserting data into the vector database and thus inserting data into the RAG system. So the next thing we'll consider now is how is this data retrieved and made useful to a typical user when it comes to fetching from a vector database or a RAG system. There are two main things I would really want you to understand. First of all, understand the similarities between a vector database and a relational database. So given a relational database like what we have here, we can easily get a particular row by providing the index. This is similar to a vector database because in a vector database, this ID are the vector embeddings of the chunk, while the rest of the column, the rest of the row, which is usually only one column, is the chunk. So what actually happens is that given any chunk, the whole chunk is converted by the embedding model into an embedding vector, and then the vector is now used as the index, while the actual text that makes up the chunk is used as the body of the row. So when a query to fetch a particular data comes in, that query is also converted into embedding vectors by the same embedding model, and then the resulting embedding vector is now compared. We perform a similarity search with what we have in the vector database, so the most similar ones are then returned, and because of this nature, we do not get an exact result from a vector database just like we would do in a relational database. For example, if you were to provide 1 here, you are definitely getting the rest of the data in this row. But for a vector database, we can't possibly expect a query coming in to match the exact text that makes up the chunk. So what happens is that when the text comes in, we pass it through the embedding model to get the vector embeddings, and then the vector embedding is compared with what we have in the table, and those ones that are most similar are returned. So that's how a vector database is kind of similar to a relational database. So now, according to this diagram, when a query comes in, like the sentence we have here, it passes through the same process of going through a tokenizer, and then we get the token. Then the tokens are now passed through the embedding model. Then the embedding model now gives us the vector embeddings. So with the vector embeddings now, we can now perform a similarity search against what we have in the vector database, and the most relevant ones are returned. Note here that what is going to be returned will be the exact chunk that was stored, and in most cases the result expected by the user giving the query is not the exact chunk but something that answers the question. So in order to satisfy this need, when we get the output from the vector database, we first of all use it as a context in a general purpose large language model like ChatGPT or Gemini. So what we will do is that we will tell the model that using our retrieved data from the vector database as context, answer this user's query. That's when a well fashioned output will be given out to the user. Now that our packages are fully installed, let's proceed to creating the tokenizer for the embedding model. So here we will not be writing the code out explicitly. Luckily for us, the transformer package from Hugging Face provides a method where we can just provide the name of the embedding model we want to use, and then it will return the tokenizer for it. So we will save the tokenizer as a file in a folder and then call it whenever we need it. So the first thing now is to import the needed class from the transformer package, and then we will now call the pre-train method from the class and provide the name of the model of which we need the tokenizer. And then after that, we now save the tokenizer we get in a certain file. Notice here that we are providing a path here to the model. This means that we will need to have this model locally in our file system here. So to get the model locally, we'll now go to Hugging Face platform to download the model. This is where we want to download the model. Don't worry, links to all assets will be provided in the description of the video. So when you head over to here, the model we want to download is this one, model.onnx. So click on the download button here, and then it starts downloading. So once it is done downloading, you will now copy it from your download folder to the folder of the project. Okay, here we now have the model file inside the project folder. So the next thing now is to run the code in this create tokenizer.py. So running it creates the actual tokenizer file. So we now do. Here you can see the tokenizer file, the tokenizer folder is created and everything we need is inside here. So what I like to do is to move everything about the tokenizer into the folder as to make sure everything is in one place. So yeah, we'll copy this and this into the tokenizer folder. Then our project structure is clean again. Next, we create the file that we'll be using to convert words to tokens and then tokens to embeddings. In order to structure the project well, I will be putting this ONNX embedder file into a folder called vector, so that everything related to vectors or the vector database will be found in one location. The next thing is we import all the necessary packages we will need to implement this class. So to implement this class, the first thing is we will need the location of our embedding model. To do this, we first get the root directory of our project, and then we now use that to get the location of our embedding model. Now we create the actual embedding class, which will extend the embedding function from ChromaDB. ChromaDB is a vector database company, so in my opinion they provide the best vector database to work with if you need something to run locally. We are going to create the constructor for the class. So what we want to do in the constructor is to initialize the embedding model and the tokenizer. So the first thing we do is get the location of the model and also get the location of the tokenizer. Then we go on to initialize the model. Note what we are doing here. This class here says inference session. So if you are familiar with how ChatGPT works, you know that each time you ask the bot a question and then it returns an answer, we will say it is running inference. That's the same thing happening here. So what's happening here is that each time we use the embedding model, we are using an inference session. So that's why we have the inference session. So we load the embedding model into the RAM of the operating system to run an inference. And then the next thing is the tokenizer. So here also note that we are doing the same thing we did when we were trying to create the tokenizer. But here, what we did here was that after providing the location of the model, there was no additional argument here, meaning that the method here was expected to fetch the tokenizer from the internet. But when it comes to this one, we will say a local files only, so not the use of local files only through here. So this one means that it should only fetch what is locally available using the path provided here. The thing we do is we create this method which enables us to instantiate the embedding class like this and then call it as a function. So when it is called as a function this way, it runs the code under the method itself, this one. So next we pass the argument for the method, which will be incoming text that we intend to that we intend to convert to token and then to vector embeddings. And next we pass in the input text, which is literally the chunk into the instance of the tokenizer we created earlier. We also specify what we want the output to look like, which will be a numpy array. We also specify other arguments which I will go into later. So for this argument, the padding equals to true here means that given any chunk, remember that the data will come in as a bulk, which is usually a page of text, and let's assume a chunk is a single line on the paragraph. So once this chunk comes in, the embedding model has a context window, the maximum number of tokens it can take in at a time. So assuming the context window is 6 and then a particular line comes in which is less than 6, the padding here specifies that the tokenizer should fill in the remaining space with 0, since the token will have taken a complete set of input. The remaining spaces are filled with zeros, like what we have here. The same thing applies to the truncation equals to true, but in the reverse case. So if a particular chunk is longer than the context window of the embedding model, the excess ones are discarded. Okay, so one thing you should note here is that the output you get here is a batch encoded Python dictionary with keys and then values made up of numpy arrays. But what we intend to pass into the embedding model should be a normal Python dictionary. So for that, we will have to convert what we are getting here into a regular Python dictionary. So we iterate through the inputs here that we get and we store it in these variables. The ORT here means when next runtime inputs. So for here we will now say create a key value pair for each key and value in the input items, and we pass in the inputs into a section of the embedding model. We also go on to specify the output that we are expecting. You should note here that the output being none here doesn't mean nothing should be returned, but it means that everything should be returned. We also have options like last hidden state, which will return the input embedding. We have options like attention, which will return the self-attention weights, and we have options like logit, which will return the scores on each token that make up the vocabulary. Then the next thing is we take the first item from the output and find the average of it. So the main reason we are doing this is because remember when I said the model outputs vector embeddings for each token. So the vector embeddings coming out for each token looks like this, but in order to operate on it, we need a single number for each of this list here. So the average here is to compute the mean for all the items in this list. So for the first token in this text, which is this, we will now have this. We will now have 0.25, and then for the next token we have this. So that's the essence of finding the mean. Then we convert the output, which is a numpy array, into a regular Python list and then return it. Note that we normally use numpy arrays for operations within a model because we can easily perform operations like this. You can see that we can just pick an array and add 2 to it, and then 2 will be added across board to all the elements of the array. So that's why we normally use numpy arrays for operations within a model. Okay, now we'll go on to set up our ChromaDB client that will help us create collection, save it to a collection, and fetch data from a collection. A collection in a vector database is similar to a table in a relational database. And now we write out the function that creates the collection. So first of all, we import everything we need, and then we go on to write the function. So this function will be taking in the name of the collection as the argument, and for tutorial purpose I will be giving a default name since that's the only name we are going to be using now, which is a knowledge based collection. And then we go on to get the root directory of the project, which we then use to specify where we want our collections to be stored. Remember, we are using ChromaDB, and I promised you that everything we'll be doing here is something you can deploy. We are not going to be using any vector database on the cloud. So that's why the collections will be stored locally on our system here. So from there, we create the folder using the path we specified above. We now tell Python to shut up if the folder already exists. We then proceed to create a persistent client. So the persistent client here means that the DB should be stored locally on our system, just like I said earlier, and we tell it where it should be stored. We also go on to create an instance of the embedding model that we are going to be using, the one we defined here. And from there we go on to return the client. So in this client we'll be using the get or create collection method. This method ensures that if the collection already exists, it will not be created, but if it doesn't exist, it is created. We specify the name of the collection, and we also specify the embedding model it should use. Then we go on to create a function that sets up the collection. Notice here that I'm calling this setup collection because if the incoming text is already chunked, then all we have to do is insert. But if it is not chunked like a PDF, then we will have to perform the chunking process first, as you will see later in the video. Then we go on to create a collection called knowledge base using the method we specified earlier. Notice here that I'm not passing in any arguments because I already set a default argument here so that we can just move faster. We then specify the data we are going to be storing in the collection. So for now, this is the format of the data. It will be a list with a dictionary as item. So here we have the ID and the text. We then store the data into the collection. Here we say pick the text for each document that make up the knowledge base documents, and also pick the ID for each document that make up the knowledge base documents. Finally, we wrap this insertion process in a try except block to ensure we catch any error that might occur. Finally, let's replace this sample data with the actual data we intend to store in the vector database. But before this, we should understand why the data should come in this format. And to do that, we have to first understand how a vector database actually stores data and how it works. We all know that a relational database can have multiple rows and multiple columns, such that if we provide the ID 2, we will get the name Emmanuel and the age 21. But for a vector database, we conceptually have only 2 columns, where the first one stores the embedding of the chunk and then the second one stores the actual chunk. Why this happens this way is because when we were inserting the chunk into the vector database, the chunk is fed into the embedding model, which provides the embedding vector So this embedding vector is now used as the index of the chunk. That's what we have here. So the embedding is stored on one column and the chunk stored on the other column. And when a query comes in, we will now pass that query text into the same embedding model, which converts it into embedding vector. Since we do not expect the query to be an exact match of whatever we have here as the chunk, we will therefore perform a similarity search to get the most similar ones. Sorry about what we have here. This should have been the first chunk, the second chunk, and then the third chunk. So the most similar ones are returned, assuming that the first and the second are the most similar. Since the last two numbers, this number here are the same, we will now return the first two alone, and that's how we fetch information from the vector database. With this knowledge, we can see here that the size of a chunk determines the accuracy of the data we get when we fetch from a vector database. Using the right stats help us to avoid what is called embedding dilution. Embedding dilution is a situation where a similarity search performed against a chunk in a vector database is very low due to the availability of irrelevant information in the chunk. So this means that we should keep our chunk as small as possible and also as meaningful as possible. In this project, we'll be designing a rack system that serves as a front desk customer service to answer relevant questions about a company. So for the company we'll be using here, this is how we'll chunk the company data. So the first chunk here is the company's overview, and then we have the mission, the services, the return policy, the customer support, the founder, the funding, and the offices. Notice here that each of the chunk here is a complete information about the company. So this gives each chunk a semantic meaning other than just randomly breaking the data up into different chunks. Then we express the company's data as Python dictionary and then use it here. So here you can see that the ID represents the subheading and the text represents the body. So with this, we have our chunk ready for storage or for insertion into the vector database. To not waste your time, go to the GitHub repo linked in the description below. Copy the embedding list and paste it into your current work so that you can proceed with the rest of the video. At this point, I think we have everything we need to test our rack system. So let's go on to create API endpoints that we'll be using for the testing. Here, the first thing we do is we import everything we need. Since we'll be using FastAPI, so we go on to instantiate a FastAPI application object, and then we instantiate a collection object that will enable us to fetch from a given collection. And we create a function that takes in the incoming query and then performs a similarity search in the collection. Here we want to return the most similar item, and what we want to return should include the actual document and the metadata. The metadata here involves extra information like the timestamp and the source of the data. Finally, we go on to return the context. Let's now create API endpoints that will enable us to create embeddings and to make queries. Before that, I would like to create a test API to ensure that there is no error in our code. Now let's run the server so that we can test the API endpoint on Postman. So if you head over to your terminal here and your visual environment is not activated, so you should first of all activate your visual environment by doing this on macOS. For Windows users, the appropriate command will be displayed on the screen now. Then go on to run this command. So here we have an error. It is saying here file does not exist, and let's see what file doesn't exist. I think it can't find the model. Let's scroll up to see. Okay, so I think the problem here is that it cannot find the model. So let's see what's probably wrong with it. Maybe we provided the wrong file path. Where we tried running this inference section was in this embedder file. So let's see. This is where the error is occurring, and this is the file. Okay, I think I see what's wrong with it. So the thing is, this was supposed to originate from this folder here, but we don't have that folder. That folder doesn't exist. The way I intended it to be was that this folder should contain everything related to the embedding model and the tokenizer. So here, what we will have to do now is we'll move this file and this file into a folder called embedded_onnx, and this tokenizer folder will also be part of it. So the first thing I will do is to create a folder here. And then I will now move this and this into the folder, and also I will move this tokenizer folder also into here. So that's how it's supposed to be. So coming back here, the embedding directory was supposed to originate from here, this embedded_onnx. So that was our problem. So let's now rerun the server. And here you can see application startup complete, meaning the problem has been fixed. Now that our application is successfully running, let's go on to Postman to test. So if you don't have Postman installed, you can just Google and check how to install it. So let's create a request here. We are testing the test API we created initially when we were setting up our first API endpoint. And to get the endpoint we are going to test, when you come over to your terminal here and scroll up, when your application was just starting up, you see here you were told that the endpoint, it is running on this endpoint. So this is your base endpoint, and that's what we are using here, and this part is the API endpoint you are using here. So that's it. Let's now go on to test to see if this message will be returned. The message is returned, so it means everything is working as expected. Let's now go on to implement the endpoints to create embedding. Before we write the endpoints that converts chunks into embedding, I want you to notice here that immediately our server was able to run successfully, this folder was created. So this folder here is where the embeddings will be stored. And from here you can see here that ChromaDB uses SQLite under the hood as the file storage system. Now let's create the endpoint. So to create the endpoint, we first of all specify the endpoints, and then we go on to call the method that is responsible for creating embedding, which we specified earlier here. We then go on to return a message to show that the creation of the embedding was successful. Let's hurry over to postman to test the endpoints. We create a new endpoint here, call it create embedding, and then specify the endpoints. We are using API/create here since that's what we are using here, and we run the endpoint. So with this message returned here, it means that the embedding has been successfully created. So let's go over to that folder I showed you earlier to see if a natural collection has been created. So from here you can see that we now have a natural collection here. So this creates a collection. The collection we specified here, remember. So it creates this collection for us. This one here, and it is now ready. We can now store something in it. To fetch from the vector database, we will be sending the user query as a request body, and to do this we first write out a schema that defines what the user query would look like. We then go on to define the API endpoint. After that, we call the getContext method, which queries the embedding and performs a similarity search. We pass in the message and then we return the result as the response. Let's now go over to postman to see if this is working, but we first have to restart the server. Here in postman, we need to create a new endpoint here and call it query embedding. We then define the endpoint, which is chat, and we specify the request body. So the text we are going to use here would be who is the founder of the company, and remember it is a post request, so we change this to post and we send. So from here you can see that it returns the appropriate chunk for it. So remember when I was comparing a vector database to a relational database, I told you that for a relational database, the data on a row can be gotten by providing the index of that row. But for a vector database, a chunk like this is converted into embeddings, and those embedding is used as the index, while the actual data, which is this text here, is now stored as the data. So when a query comes in, like what we have here, who is the founder of the company, this query is also converted to embeddings. And since we do not expect the incoming query from a user to be an exact match of the chunk, we therefore perform a similarity search instead of looking for an exact match. So we perform a similarity search between the embeddings from this query with the embeddings on the collection, and the most similar is then returned, and that's why we say we perform a similarity search. So once the most similar is returned, we will now consider that to be the result of our query. And in most cases you would want to return more than one, because there are times that the first one, which seems to be the most similar, is not what you are looking for. So with that, we can say that our rack system is currently working. As I mentioned earlier, the output here is a chunk of what we stored with a bunch of other things that we don't need. But what we need is an exact answer for the question the user is sending. An answer that says something like the founders are A and B, and not the whole chunk here. And getting this leads us to the next part of the project.